Alright, so welcome to today's video where we're going to talk about conservation of energy. So this is kind of getting in the middle of our Unit 6. Now conservation is something we've talked about before with conservation of momentum in terms of the total momentum before a collision is equal to the total momentum after a collision. Now you've also heard often in chemistry or in other parts of science that energy cannot be created nor destroyed, can only be transferred to a different form. And that's what we're going to investigate with the conservation of energy and how we can use that and apply it to different situations. So one thing we need to know is we're dealing with mechanical energy, which is the sum of the kinetic energy and the gravitational potential energy if there's no other form. So if there's no thermal energy or sound energy or waves or anything external, we're just dealing with things related to its position and how fast it's moving. So kinetic energy and gravitational potential energy, and that's key to being able to solve them in a simple way. Now, we're going to go through that example in class, but let's just take a look at what the end result might look like. And you're going to notice that the change in EK is equal to the change in the potential. So the change in the kinetic energy from one situation to the next is the same as whatever change in potential energy happens. So those two things are related to each other, which can be expanded to figure out EK minus EK 0, or we could use prime notation like we did with momentum. So EP minus EP 0. The whole point of this is to come up with an equation similar to that of conservation of momentum, where we had something before and the things after, which we can do, and it comes out to be the same type of idea, where we have the energy before is equal to the energy after. So the total energy in a system before is equal to the total energy in the system after. Because we can't create it, we can only put it from potential to gravitational and gravitational to kinetic and back and forth as the situation evolves. If you prefer to use the prime notation like I typically do, this would be written as EK plus EP is equal to EK prime plus EP prime. Now that's, again, it means exactly the same thing, just the total energy before is equal to the total energy after. So let's take a look at how to use this. So we have a 25 kilogram boulder falling from a 1.0 times 10 to the 2 meter cliff on the sea to sky highway. What is the potential energy at the top of the cliff? So you got a little diagram there. It's 100 meters high. We're assuming that it's not moving at the top because it's just going to start falling. Just kind of rolling off the edge, or it was attached and it's going to fall. So what is the potential energy? So we're just going to go with EG is equal to M. Again, see, I've gone back between EP and EG, and that will happen. They mean the same thing, so just be aware of that. And we know the mass, and we know gravity, and we know that it's 100 meters high. And we can calculate that fairly easy to do 2.4 times 10 to the 4 joules after doing a bit of sig figs. So we've already done the first part, but that's not been using our conservation. So let's get into part B. What is the final speed of the boulder as it hits the highway? So we need to find V. All we know is the potential at the top. So this is where the conservation energy comes in. Got E, I'm going to go with G just to be consistent with part A, equal to EG prime plus EK prime. Now before you go further, you always want to see if you can make anything zero. It's best to always pick a 0 point where it makes sense. The ground in this case is the easiest place to make 0. So that means our potential after, which is when it hits the highway, is going to be 0. And if we're assuming that it's starting from rest at the top, our kinetic is initially 0. So we're left with that Eg is equal to Ek prime. We have a value for Eg, so we don't need to worry about it. So let's put in our equation for kinetic energy as RV squared. And now we just have to rearrange, which will look like this. Or you could divide by a half m, it means the same thing. And at the end of it, you will get 2 proper sig figs, which would be 2. It's going to be 44 meters a second. And then let's take a look at C. What is the speed of the boulder a third of the way down? Now you have to make sure you're thinking about what that means in terms of its final height. A third of the way down means it's gone, there's still 2/3 off of the ground. So your height is 2/3 of 100, which would be 66.6666, but I'm actually going to leave it as 2/3 of that h, just because that's easier to write than 66.666666 meters. Now, the same situation here, we're going to start with our same thing. Eg plus Ek is equal to Eg plus Eg prime plus Ek prime, starting at the same point. But now we have to think about if there's anything 0. We're still starting from the top of the cliff where it's not moving, so that's still 0. But at this point, we're not all the way to the bottom, and we're still moving, so our after, neither of them is 0. It doesn't, it just complicates the equation a little bit, but it doesn't mean that we have to do anything to advance. So then we just want to put in, we know Eg. Eg is something that we know, so we can leave that there. We know that the V is hidden in Ek, so we can bring over the minus Eg prime, put in some equations that we know. Eg minus mg, as is going to be 2/3 of h, is equal to 1/2 times mv squared, and we'll just label that v 1/3. And we can rearrange this, which will work out to being v 1/3 is equal to the square root of 2 times Eg minus mg 2/3 h over m, and that's all square rooted. And that's going to give you an answer in the end, again, to 2 sig figs is going to be 26 meters a second. So make sure you calculate that out to see if you get that same answer. It's just a complicated rearranging. Do it one piece at a time, and hopefully it will come into place. There's going to be a second video that goes over the next example because it involves the conservation of momentum that we dealt with in last unit. So we're bringing conservation of momentum and conservation of energy together. And as always, physics is indeed awesome.